This lesson, we're going to look at correlation between two different variables and regression. Particularly, we're going to look at linear regressions. A correlation is when you have two different variables and the values of one are somehow associated with the values of the other variable. Way back, we talked about a lurking variable, and I had pointed out in the discussion that, increases in drownings and increases in ice cream sales tend to happen during the summer months. So there's a correlation. They both increase at the same time. However, that does not mean that there's any causation between those. There's other lurking variables. So we want to be very careful to point out that correlation is not the same as causation. Now, a linear correlation is when we have two variables, and if you look at the plotted points, there's somehow an approximated straight line. It doesn't have to be perfect, but fairly close that we have this going on. So what this might look like, these, even though they're scattered about, you can see that as X increases, Y increases. Now I'm just going to kind of put that on here. X increases. As Y increases, you will have homework questions that ask you what is going on when you have a positive correlation. So I'm going to say X increases as Y increases, and just kind of write that on here like that. And that means that it's going up. From your algebra class, you may remember that lines that kind of head up have a positive slope. So the slope is not necessarily the same as this R number here at all, but we are saying that R, which is a correlation coefficient, it kind of measures the strength of this correlation. R is positive, also kind of corresponds to a positive slope. Here we have a negative R and we have a negative slope. So if we were to draw a line through them all, so as X is increasing, as you go to the right on the X-axis, X is getting bigger, but the Y value is decreasing and getting smaller. That makes a negative correlation then. This is not necessarily slanted a lot more than this one is. So besides the positive and negative, notice how closely the dots are packed. If we put a line on here, some of our dots are fairly far away from it, whereas if I were able to really cut a line through there, I haven't drawn it in a very good place, the distance between the lines is smaller than the distance, and I said between the lines, but I mean the dots, the distance here. So this negative one is more closely packed, which is why the absolute value of this is closer to 1. Now I know this is negative, but the absolute value of it is just the 0.971. The absolute value of this one is 0.859. When we look at absolute values of R, the absolute values that are closer to 1 indicate a stronger correlation. Now here, this just kind of looks like you took some buckshot and randomly hit a target with it, birdshot. There's no correlation, which is why this value is so close to 0. Now this value is not strong, but it's stronger, and that's because there are sections of it where you can kind of hit it with a straight line, right? But what really happens is that we have almost a quadratic relationship, like a parabola. But for the purposes of this lesson, we're simply going to say it's nonlinear. There's a pattern there, but it's not linear. Okay, so our linear coefficient that measures the strength of the linear association between two variables in a sample is R. That is for a sample. If you wanted to deal with a population, okay, it's different. Just like we had X bar is the sample mean and mu is the population mean. We have P hat for the sample proportion, and we have P for the population proportion. When you're looking at a population here, you get this symbol, which is, of course, a Greek letter, and it said rho. If you look at the pronunciation rho, you can see that it starts with an R, so it's somewhat related to the R we have here. However, if you look at the symbol itself, it kind of looks like a P. So maybe that will help you remember that this is the one that goes with the population, but because it's that correlation coefficient, its cousin is R, and we say this one rho, okay? As we go through this, let's talk about what will happen with that linear correlation coefficient. They're always going to be between -1 and 1 inclusive by the way they're calculated. Okay, so you should never get a correlation coefficient less than -1 or greater than 1. If you took all of the values of the variables and you converted them to a different scale, R would not change. So what's a different scale? So like if you had a correlation coefficient for something that was measured in feet and you changed it to inches, correlation coefficient wouldn't change. If you had issues of things that were measured in degrees Fahrenheit and you changed them over to Celsius, the R would not change. So it's immune to what you're measuring by. It's also not affected at all by the choice of X or Y. If you had something where you said, well, as the ice cream is increasing or the ice cream consumption is increasing, so is the number of drownings, and you had drownings on your Y, you could turn that around and say the number of drownings increased, so does ice cream consumption, and it would not have any effect on your R. Now do keep in mind, R only measures the strength of a linear relationship, not other ones, which means back here this value is really low because this is not truly linear. But if we looked at a measurement for a quadratic regression, we would get a really high value here, but R is not what you use for anything except for straight lines. And it is sensitive to outliers, which this should have said it's not robust. When it's robust, then things don't change a whole lot. If it's robust to normality, then if it's not normal, it doesn't change a lot. If it is not sensitive to outliers, we would say it's robust. But when we have outliers on here, it is certainly not robust. Whenever we are doing a hypothesis for linear correlation testing, you don't have to use any greater thans or less thans. Okay? If you're looking at linear correlation, what you're really determining is that our null is going to be that there is no correlation. That's actually what that means. If we say that rho is equal to 0, that means that there is absolutely no correlation. And that would be your null hypothesis. Then the alternate hypothesis would simply be that there's some correlation. We're not saying if it's strong, but we're simply saying that there's not none. So there is some correlation. And you don't have to make any guesses about this or anything. This is always the way you're going to write your hypotheses. The null is that it equals 0. The alternate is that it doesn't equal 0. What are the requirements then here? When we did our last one, we had to say that it was a simple random sample, and we had to have either normality or greater than 30. Well, here we also need a simple random sample. But then notice that both of these next two say something about visual examination. Now, if we were really like research level statisticians, we wouldn't just be doing a visual examination. This is just kind of an easier application that pretty well meets what the actual requirement is. So let's not go into making it harder than it has to be. You're going to do a visual examination of the scatter plot. And so you're going to have to do a scatter plot of these unless they tell you that this information happens. And what you're looking at on the scatter plot is that there is a straight line pattern and there are not outliers. Now, what is an outlier? An outlier is one of those dots that's just way away from all of the other ones. It might be a mistake, or it may just be an anomaly of something totally unexpected. So if it's a mistake, you remove errors. Okay, if an outlier is a mistake where you just say it's just impossible, this point is correct, you would remove the outlier. On the other hand, if it is a true measurement and you don't know that it's an error, you leave it in there. And sometimes what we do is we actually calculate it once with it in there and once without the outliers in there so that we know what effect that outlier is having. So you should consider effects if there are outliers and you don't know that they're errors. Linear correlation coefficient can be computed for any paired data. This is kind of a caution for you. So just because you can find it doesn't mean the requirements are met. Again, I'm going to take you back to this slide. Here, there was a calculation and we found an R value. But it should not apply to this because we do not meet the requirement that they look like they're in a straight line. So you can always apply it, but that doesn't mean that you should. There are some really ugly formulas for calculating R by hand. So we're just not even going to put those on the screen. You're going to need to use technology. So we are going to round the correlation coefficient R to 3 decimal places. So if you just read what I've underlined, round R to 3 decimal places. The 3 decimal places is so that we can compare that to the critical values that we typically take out 3 decimal places. And notice these say or equal to. They cannot be both equal to. So that's got to be a typo. If it's less than or equal to alpha, it does support the claim. If the p-value is greater than alpha, this is the one that should not have it on there, okay? If the p-value is greater than alpha, it doesn't support the claim. Now, what is the claim? Because I didn't mention that earlier. I did tell you what the hypothesis always is, but notice it does say here that the claim is linear correlation, and the claim is linear correlation. So our claim is going to be that it is got linear correlation. There's a large list in the textbook online about countries and the chocolate that's consumed and the number of Nobel laureates they have. And of course, it would be ridiculous to think that if you have a lot of chocolate consumption, you're also going to have a lot of Nobel laureates. But that doesn't mean we can't graph it. You can graph things that we know don't necessarily relate to one another in the everyday sense, but yet we might can find a correlation. So if we take these values and we put one of them over here on the X and the other one on the Y, and this has got chocolate on the X and the Nobel numbers on the Y-axis, then we can graph these points, okay? Now, how do you graph the points? And the reason you'll have to is because one of the things we want to do is a visual inspection of the scatter plot. Now, possibly when you're online doing your homework, you can just open in StatCrunch and go to the graphs and tell it that you want to do a scatter plot. But if you need to do it yourself, you're going to hit your Stat menu and then go to Edit. And that's going to bring up List. And I'm going to go ahead and do this again just so you can see it. So if we go Stat, Edit. Now, I have a list of numbers in here I don't need. When you want to get rid of a list, go up and hit Clear, Clear, Clear. Do not hit Delete or your list is going to hide from you. It doesn't really go away, but it does go where you can't see it. So I hit Clear, Enter. Now my list is gone. Then you're going to enter the numbers. So these values, I just put the values from my chocolate in the first column. And then the values from the Nobel in my second column. I have to enter after it. So you should have the exact same number of values in both columns. If you don't, you've made a mistake somewhere. Okay, now when I hit graph right now, it's probably not going to graph. Oh, it did. But let me tell you why it did. It's because I have stat plots on. And the way I can tell I've got it on, if I go over here, see how that's dark? That is coming from a stat plot. So the instructions that are right underneath here are telling you how to turn it on and off. So get to that stat plot, you go second y equals. Second y equals. So when I hit second y equals, I get to this thing about statistics plotting, and you can see on your own calculator just above your y equals it'll say stat plot. So I have mine turned on, but the chances are when you very first go there it's turned off. So right now I'm just going to hit enter even though mine's on. You will want to make sure yours is on. And then you have several different types of graphs you can choose, but we're wanting to look at a scatter plot. So that is this very first type. My X list is what I put in L1. My Y list is what I put in L2. That should be there automatically for you. If somehow it's not, you can enter it. So right here, if I didn't have L1, if it doesn't have your list 1 and list 2 there, then the second function of stat brings up a list for you. So second stat, and then you can just choose the one you're wanting. So like I can just click L1 and then it puts it there. So if it's not already there, you can enter it. That was second stat to get to list, and then you can do L1. I already have these here. You can decide what you want your markings to be. It doesn't matter if they're little dots, big dots, pluses, whatever. That's not important. But now I'm going to hit graph. Now, if you don't see it, even though you've done these steps, it could be your window. So when I go into my window, I can adjust those based upon the numbers I have. So looking at the list of numbers, and I'm looking at them right here, these were 4, 5, and 6. That's the only numbers I had. So I could say make my minimum, well, I don't want it to be 4. I want it to be smaller than 4. So I could go from 3 to 7 so that they would all end up on there. And then the Y values, I can look at those also and say, oh, well, my smallest Y value is a 2, so maybe I'll let them start at 1 so I make sure I can see that 2. Don't recommend that you start at your value, but you go a little past it. My high value is 11, so I'm going to let it go all the way to 12. And now when I hit graph, I'm going to see it more centered up there. A normal viewing window, you can hit zoom 6 and go to a normal window, and that goes from -10 to 10. So you're not seeing your last dot 11, but you can just adjust that window as you need to. Okay, so this is the graph that we essentially get, and that was settings I happened to have on it at the time. Now, one thing that's a problem on this one is that I put my Y maximum at a 10, but my Y maximum should have been 11, but it would have had 5, 1, 2, 3, 4, 5. And then instead of stopping here at 10, it would have gone up to 11. So I actually have another dot that should be right there. Okay? This is all just to meet the requirements. Visually speaking, does it tend to fit a basically straight line? And I would say yes, it does. Does it have outliers, visually speaking? Well, it does have some that are a little lower, some that are a little higher, but it doesn't have any way off. So I think we're okay with the outliers. Okay, so that meets our requirements. So once you've met the requirements, we've got to look at how to calculate it. So this is that same list of numbers, and I know that there's a lot going on here, guys. You may just have to take a screenshot of something for how to do the calculations or how to enter those. But we already got our list of numbers in here. So you don't necessarily have to do that again. Okay, you've already listed those. So how do you do the calculation? That actually starts right here at the test. So you want to go to test, which is stat test. So it's stat, and then you have to go to the right to get to test. And then we're going to do a linear regression t-test. Now, it's the only linear regression test you have, so you're not going to pick the wrong one. Just linear regression t-test. So this is t. We tell it to pull the values from L1 and L2. And again, always on this particular type of test, you're going to leave it here. It does not equal 0. Okay, does not equal 0. And then you hit enter, and you get this stuff. So again, I'll bring up the calculator, and we're going to do that. So I'm going to quit my graph. I'm going to go to stat, over to test. That LinReg is not showing on my first screen, so I have to scroll up or down until I get to it. And it's quite a ways. Okay, it's F right here, LinReg t-test. So I just had to scroll to get there, hit enter. That's where you're seeing this. And the only thing I need to change here is make this not equal to. Because we were always looking at it's either equal to, that was our original hypothesis, or it's not equal to. So I'm going to hit enter, and I'm going to tell it to calculate. So this is exactly what's showing up over here. So that's how to get that information, and then let's talk about what that information means, okay? Now, you want to scroll down on that. I guess I could mention that because you're trying to find the R value, and it's not showing on this screen, but this arrow down means there's more information below. So you just click that until you get all the way to R. And that is the R calculation, or that correlation coefficient that we're trying to calculate this time. Okay, so this gives me that correlation coefficient. And of course, I would round that to 5 at the end, 0.795. Now, I know that that was a lot. So why did I do that? Because if you wanted to do it by hand, you have to take your original values, and then you have to add all the original values. You have to square each of the original values. You have to add the sums of the squares. Then you multiply the original values, and then you add all of those products, and then this is your formula. That is so tedious, okay? You don't want to do that. It comes out to 0.795. But this came out to 0.795. Don't you love your calculator? I just love these calculators. Okay, so once again, by the way, this has got the typo on it. It was supposed to be if P is less than or equal to alpha, it supports the claim. If the p-value is greater than alpha, it does not support the claim. Okay, look at our p-value then. On this particular listing, this was our R, but not our p-value. So I'm going to pull back up my calculator here. The p-value is listed at the top. So if it asks you for the correlation coefficient, it's way down at the bottom. But the p-value is right here, 0.10. That's going to round to 80. 0.1080. So let's look here. We know that the p-value for that particular one was 0.1080. Now, we would have to know alpha so that we can make the comparison of it. Generally speaking, we've been looking at a 5%. I don't actually think that this one told us at all what to test, because it was just find the correlation coefficient. But as far as learning to use this, if, and that's what we're going to say here, if alpha was 5% or 0.05, then the p-value is greater than alpha, and so we would say does not support the claim. However, that was just when we had a few values. Again, in the chart, there's actually lots of values, okay? So if we take all of these values, not just the 5 that we had before, and we start to look at that, once you have more in your sample data, you can redo the test. First of all, is it random on the requirements? Well, there's no reason to think that it's randomly selected because it didn't tell us it was, and it didn't tell us how it was used. Okay, so it doesn't appear that it's random. So we're going to say right now the results may not be valid because we didn't clearly meet the the first requirement. Okay, we would need some more information if we know if it's valid, but it does kind of have a straight line pattern. Okay, we kind of have this line that kind of heads up in between there, and because these are fairly well balanced on both sides of that line, and by balance I'm saying we can draw perpendiculars, you know, above, below, and kind of see where we're going. There's not any huge outliers. It's not way away from everything else. Okay, so our other requirements, they're fine. So if we take all of these values and put them into a huge list in our calculator, okay, and I've said on a previous slide how to get to the list. Oh man, I had this typo throughout, didn't I? That's just horrific. I'm embarrassed. I wish I had time to redo it, but I really don't. Then what we want to do is with this, which this one's different than our other one, but what we see here is the p-value of this. Now don't forget this e to the -6 actually means that that is essentially 0. Oh, I don't have it on red yet. So that rounds off to 0.0000 because this would move that decimal 6 places to the left. Okay, and that value then, if that is p, that is definitely less than alpha of 0.05. So in this case, once we put all of these samples in, since p is less than alpha, we're looking at this conclusion. So see, having more data actually changes the conclusion. Okay, so the amount of data makes a big difference when you have this. Now, if we were going to use critical values, okay, you're looking at your critical values, both positive and negative. Now, the reason that they're both positive and negative is because always on this, we ended up with a two-tailed test. We said it's not equal to it, okay? So you've always got two tails. So what happens if you're dealing with critical values is you look at least the symbols right here. You look at how the absolute value compares to the critical value. The R can be found on your calculator, and we've already talked about that. It's at the very bottom of that display. But unfortunately, you cannot get your critical value for R out of your calculator. You have to get it from a table. Now, there's a full table in the textbook on page 706. However, when you're actually doing your homework, there will be something, I believe, on all of the problems that you can click to see a portion of the table. So this is a tiny little portion of the table. What happens in one column of it, you can choose N. Now, the actual N we had, notice if this is degrees of freedom of 21, I actually had N equals 22, okay? So my N value would have been 22, and that's not on the chart, okay? So what happens is that I know 22, 21, 22, 23, 24, 22 happens right here because if we were counting it out, 20, 21, 22, 23, 24. So it's just a little below that halfway mark. So I know that it's between these two values, but not exactly in the middle. It's somewhere close to right here. So you're kind of guesstimating on that critical value if you're using a table like this. Now the alpha, there are lots of columns for different alphas on that table, so you would just look for the alpha that said 0.05. I might can bring up a fuller version of that table for you to see it, but I don't have a great one because it's not exactly like it is in the textbook. Critical values for R. I do have one type of one that I can show you. It's just, I think the heading of it is slightly different than what they have on there. Oh, well, see, that's not even all of it. I tried to take a picture of it from the textbook, but it actually didn't save completely. So, but you can see this. This is from the textbook. Here's 20. And here's the 25. So that's exactly what I took a snippet of right here with my alpha is 5. So you'll have lots of values of n, and you have different columns. So like the next one over, I think is 0.02, and then we go to 0.01. So we have different alpha values there. Okay, so back to our PowerPoint. You're just going to have to guesstimate and say, well, it's somewhere between 0.4444 and 0.396, but it's got to be just slightly closer to this one. So if I were guessing right now, I might say 0.42, but we're not sure. Now what happens is when we have our critical values, we have a positive one and a negative one. So we would say there's one over here on the left, it may be negative 0.42, and one on the right. Now thankfully, we're not in a real close, tight situation here, because if I said it's 0.42, which might not be precise, then I could say, well, negative 0.420, and that was supposed to be a negative, and then positive 0.420. But what happens is my R value, that 780, is way out here, okay? So again, it is in the critical region. And since we're in the critical region, okay, our absolute value of R is going to move out here into the critical region. So since it was past it, we say that there is sufficient evidence to support the claim of a linear correlation, which makes sense because this is quite a bit closer then to 1. You know, and the closer your absolute value of R gets to 1, the stronger your correlation is. All the same, do keep in mind, correlation does not imply causation, okay? Now we're going to talk more about linear regression in the next lesson and how to find linear regression equations. Hang in there, we just got a couple of lessons left. Get in touch with me if you have any questions. And again, I apologize for those typos.